In this video, we're going to be talking about the phylogenetic tree. So the phylogenetic tree basically shows multiple species could have had a common ancestor, but then due to some kind of evolutionary change or evolutionary history through climatic change or change in food or whatever the consequence might be, it ended up having the species adapt towards that certain environment. So we're going to be looking at two different examples. The first example, let's take example of Homo sapiens, Homo neanderthalensis, and Homo erectus. So if you understand from the genus over here, we have Homo plus sapien. Okay, Homo is the genus, and sapien is the species. And we also have Homo neanderthalensis and Homo erectus. Since they're all part of the same genus, that theoretically proves that they must have all had one common ancestor. However, because these species could have migrated or a change in their habitat or food or diet could have probably caused the species to a different, like one part of the species to adapt towards that change, and because of that we end up with species A, and this part species B. So when we end up with species A and species B, we get over here species A, which is just species 3 in this situation, but over here the species B, some other change must have happened too. Either that's climatic or diet or habitat, whatever it is, we end up with species 2 and species 1. So if we were to apply this to Homo sapiens, Homo neanderthalensis, and Homo erectus, then, for example, they must have all been part of some kind of family, this large family, but then due to climatic, habitat, or diet changes, we could have Homo erectus over here, but a different kind of species we'll call species B over here. However, this species B must have changed, leading to Homo sapiens and Homo neanderthalensis. This change could have been climatic, habitat, or diet. But whatever it is, the phylogenetic tree just shows how the species evolved due to some evolutionary history or evolutionary change. And it shows the history of how the species were once connected, but eventually changed. But this just proves how all the species could have had a common ancestor. And if we were to take every single species in the world, if we were to take the phylogenetic tree of every single organism in the entire earth, it would all lead to one common ancestor. And this common ancestor, like theoretically, we would probably think would be bacteria, because bacteria is the building blocks of life. So let's look at this one over here. This one not only shows the change from the evolutionary change, but also shows how it evolutionarily changed over time. So this is a lot more complicated, and we're going to be getting way more in depth through this process, to the second one over here. We have the original species, the common ancestor over here at the bottom, but then some kind of evolutionary change must have happened, which allowed the species to turn into a vertebrate. Because of this, and then what happened was another evolutionary species created a bony skeleton. Because this created a bony skeleton, half of the species must have not been affected by this bony skeleton, but the other half must have had this bony skeleton gene inside of them. So that's how we get this. So we get sharks, and we get this entire part over here. Let's see vertebrate. All of these animals are vertebrate, and we see bony skeleton from the ray-finned fish to these birds and dinosaurs over here. All of them all have a bony skeleton. But sharks, they don't have bony skeleton. They have cartilage. Hence, they're not under this entire section. We can also interpret that sharks are the closest to this common ancestor than any other organism in this entire place. So we could infer that this is closest. Okay, so now let's move on. A common change must have happened, making all this bony skeleton, and then this common ancestor must have developed 4 limbs. Of course, the ray-finned fish doesn't have 4 limbs, but these other organisms do have 4 limbs. And we can check that because when we count all the limbs, they have 4 limbs. Now, that means that ray-finned is the next closest ancestor to this common ancestor over here. And this entire process can continue to happen, and we would get more and more deeper and deeper. But the more like changes that happen to these organisms, the more further away it goes from actually being closer towards the common ancestor. This is a very complicated series of phylogenetic tree, and this happens over a series of evolutionary changes, and this shows the history of how organisms, how close they are to the common ancestor, like sharks are closest in this situation, but it also shows the history of how these organisms developed into their what we now know as their characteristics. And these evolutionary history is always changing, and we have to update it a few times every couple million years, so that we will be able to get the most accurate results out of it. If you were to wonder about the taxonomy, how would that also change? The answer would be yes. The taxonomy also changes based on evolutionary history, because back then, if we were to take the taxonomy here, we wouldn't have sharks, ray fin fish, amphibians, or all these other organisms, because they haven't developed yet into that evolutionary history due to either climate, habitat, or diet change. But whatever it is, eventually what happens is these organisms like sharks and ray fin fish and amphibians started to occur because, one, they eventually got vertebrae, they got a bony skeleton, they got 4 limbs, and then they got an amniotic egg, hair, and 2 post-orbital fenestrae over here. So that's how eventually it changes and changes over time, and we get more and more species. So obviously, when we were to look at the taxonomy over here, eventually we would have to add more and more, or we would have to change from a related species so that make it more accurate as possible. This is all about the phylogenetic tree.